Hi everyone, it's week 11 of machine learning, and today we're going to be learning about decision trees and ensembles. These are both methods that you should know about because decision trees often are thought of the way that humans embody their intuition in making decisions, and ensembling is a way of combining several machine learning algorithms together. In fact, decision trees are like a lot of trees in computer science in combining different parts together, and we have magnificent trees here in Singapore like the one behind me. Let's take a look at how this works. Let's first recap what we learned about SVMs. SVMs stand for support vector machines, which are linear models that try to find the optimum separating hyperplane between the positive and negative classes. By optimal, we mean that it places the most distance between the positive and negative points. So the right-hand side version of this is a support vector machine. We've maximized the margin such that only the support vectors, the blue and red points that touch the hyperplane, are maximally separated. This has the great generalization capability because a point such as this red one over here that is incorrectly measured within any of the locations within the red circle will still be properly classified. Compare that with the right-hand side where we draw the same circle, where you can see that if we happen to put the point somewhere closer to the blue point over here, it will be incorrectly classified as a blue point. We saw that we can solve the support vector machine optimization problem as a quadratic programming problem. We have to introduce the idea of Lagrangian multipliers, these alphas that we have here, as a way of finding an appropriate hyperplane boundary. We saw that when the Lagrange multiplier is greater than 0, that we actually have a support vector defining and holding up the hyperplane. In practice, we rarely use this idea of a hard SVM that we have up here. Instead, what we'll use is the soft SVM, which tolerates obstacles with some penalty, modeled by per point slack variable xi, indexed by the particular example that's violating, for example, j here. In these cases, for example, the red point here, the blue point here, are both on the wrong side of the hyperplane, but we've accepted them in order to draw a linear classifier. We also understand that the SVM relies on a kernel. This you can think of as a metric that calculates the similarity between two particular points. You can see it here in our definition of the Lagrangian optimization problem that we use for the hard SVM. This quantity where we're multiplying one point against another is a way of defining a kernel which calculates a similarity between the 2 points. The higher the inner product between these 2 points are, the more similar those 2 points are to each other. This general idea of a kernel is helpful in multiple machine learning algorithms, including SVMs. And we can use it in an SVM to effect a nonlinear transform, which gives SVMs their snake-like appearance in higher dimensions. Again, the important part of this is even with both soft SVMs and kernelized SVMs, the support vectors define the complexity of the hyperplane. So for example, here in this diagram, we have 5 circled points, which means the complexity of this particular hyperplane that's defined by the soft SVM is in proportion to the number of support vectors, or 5. Having more support vectors means that the classification boundary is more complex and therefore will generalize less. Now let's forecast what we are going to learn this week. We're going to understand and implement the idea of decision trees, a very simple concept that has immediate rational understanding with how most people make decisions. We're then going to look at the concept of information gain as a way of choosing optimal attributes for the decision trees. Decision trees look at one particular attribute at a time. Once we have decision trees mastered, in the post-lecture we're going to be looking at methods for ensembling as a way of integrating multiple classifiers. We've actually studied one method for ensembling already, which is the stacking idea, which is apparent in neural networks and deep learning to great success. We're also going to understand boosting and bagging as basic techniques for extending the idea of ensembling, and we're going to see how boosting and bagging play out in two particular algorithms that is applicable to decision trees, namely Ada boost, which is related to boosting, and random forests. That's an example of a bagging algorithm. Let's get started now.